say thanks to Regional Center IGNOU, Nagpur, for inviting me to share the thoughts on Diode to Nanoscale Transistor and an overview. Firstly, we would like to congratulate ourselves to India that our Honorable Prime Minister is going to laying down the foundation stone for the three semiconductor fab labs. Out of that, two labs are in Gujarat and one is in Assam. So, what is meant by semiconductor? We will start from that moment. How the diode and transistor plays role in semiconductor manufacturing. What is meant by that fab lab? How it is going to be useful for the India's development. So, a chunk of all these things we are going to cover in this webinar. This is actually a very short notice. Actually, I work on Cadence tool, Mentor Graphics, Xilinx. Those who are the mostly important and renowned tools for the fabrication of this semiconductor. Actual physical fabrication of every chip is done and processed through that first EDA tools. So I am lucky to have exposure on that Cadence lab, Cadence tool. I worked there for 6 years on a Cadence tool. Along with that, I work in different domains, analog, digital, along with the IT sectors. So I welcome all the participants to this webinar. So we'll move to the first agenda, understanding the journey of the diode to nanoscale transistor. What is meant by this concept from moving to diode to nanoscale transistor? It is a generic name given to this concept is very large scale integration, or it starts from the SSI, small scale integration, MSI, medium scale integration, very large scale, ultra large scale. There is a scaling, and we are integrating n number of millions number of transistors in one single silicon chip. This is the beauty of semiconductor manufacturing. That's why we are going to know the reducing the size of the devices, electronics devices, capability of holding the data in the devices. We are able to increase the capability as well as the scaling down to the power required for that. So we'll move to the journey, how this is journey going on, and how this semiconductor manufacturing will helpful for the India's development. So firstly, we will move to the main agenda of today's webinar, that is India Semiconductor Mission. Honorable Prime Minister has said and laying down this foundation for three labs. Basically, I would like to say one thing which is unknown to, I think so many of the students are not aware about that Semiconductor Complex Limited, which is situated in Mohali, Chandigarh, Punjab. Actually, the first fabrication lab for the small scale integration was established in 1983, and still it is going on in Mohali. There they manufactured some semiconductor devices for the defense purpose. See, we are dealing in semiconductor since 1983, but due to the lack of fundings, lack of skilled resource for that development, lack of the environment, whatever the different type of environment required for the semiconductor manufacturing, as well as the raw material to extract the semiconductor. That is the main things we required. So now after 83, since the lab is going on, we came to know that the importance of semiconductor is going on and increasing day by day. We are moving for the globalization. We are moving for the smart manufacturing, smart cities, smart grids, smart hubs. Everything is going to be in a smart way. So what is the requirement for making all the things smarter? We need some sensors, actuators, and devices. How these devices came into existence? Just because of that semiconductor. So main core part of all the globalization and the modernization of the society with the help of electronics devices and the ICT, internet along with the computer systems. So we need to manufacture. This is the main agenda. So how this semiconductor mission will helpful for the strategic importance. If you are talking about the strategic importance regarding this modernization of electronics, so it is a mostly whenever we are using any type of devices, just like a mobile phones and memory cards, whatever the data, SIM cards, even the SIM start from the SIM card, you, everything is need it requires the basic semiconductor material to hold the data. So to manufacture that, it is an important and crucial part. If we are relying and we are depending on the other countries like China, Korea, Taiwan, Japan, USA for importing all these things from there, so somewhere we are lagging the security system. What they are integrating inside that, as per our requirement, they are going to build all the things, but we don't know the exact internal structure of that particular chip and all these things. So there may be violence, there may be a data capturing moment happened in that moment. So the strategic importance of this semiconductor mission is to secure the national autonomy of the electronics devices. Along with this, economic growth is the most important factor. It is vital for driving the innovation, investment, and job creation. If we are able to fulfill this requirement of semiconductor manufacturing, so definitely our economy of the country will get improve, and lots of innovation will be there. So many products we can develop by ourselves as a ASIC, application specific integrated circuit. For the specific application, we can build our own circuit, we can get it manufactured. This is the beauty of this semiconductor mission. Ultimately, if you are sustainable and we are able to manufacture these devices, semiconductor devices in our own country, so dependency reduction will be definitely there. We will become a technology leader to foster the indigenous R&D and D and manufacturing in India. If you fulfill this semiconductor mission, so this is our national priority. So as the PM, our honorable PM Modi sir said, Atmanirbhar Bharat, Make in India, Made in India, so many digital India. One more thing I would like to add, our colleague Dr. Kumarwar, he was previously associated with GC Karad. He is the first person who has taken initiative for digitization of GC Karad. So see, this is the beauty of going with the technology. GC Karad was the first engineering institute, government engineering institute in Maharashtra, who has started the digital uh, acceptance of the payment, no physical acceptance of the payment. And we are lucky to have, you are also lucky to have Dr. Kumarwar with you in IGNOU. He has taken the initiative for the digitization of payment. So such type of improvement, that is called Atmanirbhar Bharat, as our PM said. So we are moving toward the globalization along with the technological development. So many jobs will be created with the help of this semiconductor mission. So to fulfill this crucial requirement, we have to stick to the technology. We need to understand what is technology and how to go for that technology, how to grab the opportunity in this type of semiconductor mission. So I will brief out the basic about the diode and transistors. Diode is a device. It is having a p-n junction. Uh, it is a fundamental semiconductor device. There are lots of applications of the diode, just like a rectifiers. You can every uh, made a power supply. You can use that. Diode works in a one direction only. If you supply the positive and negative supply to the diode, it works in a one direction, and reverse direction the current will not get flow. So basically, this diode is a basic element in the semiconductor manufacturing as well as the electronic circuit. If you connect the two diode back to back, we can form a transistor. So this is the just generalized concept I would like to explain to the students, those who are new and not familiar with this, how this journey of diode to semiconductor manufacturing. So if you connect this two diode PN and NP back to back, so we can get the formation of the transistors. So if we are able to make the transistor, so transistor can make as a work as a switch. Transistor can be used as a amplifier. Transistor can be used as an oscillator. There are lots of applications which we can go with the transistors. If whatever the semiconductor technology we would like to manufacture, the basic of all these things to understand the basic nature of diode and transistors. If you are able to go for that layout and schematic design, Uh, this is one way to go for the manufacturing, and another way is using the hardware description languages, just like VHDL, Verilog, System C, Blue Spec Verilog also. So, how this transistor help for the semiconductor revolution? So, we'll move to the next part of this webinar. So, there are two types of transistor: bipolar, FET. These are the basic transistor types. We can go for the scalability means number of components can be integrated, and we can do lots of things with this multiple uses of the transistors. It requires low power, that's why we prefer to go for this layout. So now we came down to the minimizing the state and the state of art manufacturing technique. So that is a new current scenario. This FIN, that is finite uh, field effect transistor. So we are going to scale down the structure layout of that particular transistor. If we have a big bulk unit of any heavy equipment, just to consider a simple example. So it requires a large, huge power requirement of that bulky device is very high. If you go for the smaller unit, what will happen in that case? Ultimately, the power required for to drive that device will be less. With the current flowing through that, whatever the electrostatic control discharge, uh, there is a less chances for that. And along with this pin FET technology, uh, we are reducing the chances of electrostatic discharge, as well as short channel effect we can minimize, and we can scale down. That means on a single chip we can place n number of transistors over there. So if we are able to place the n number of transistors in a single chip, then the complex circuit can be encapsulated in one single package. So mostly the nanoscale transistors are used in microprocessor design. If you consider the architecture of the microprocessor or a memory, the very basic unit of the memory is a flip flop. If you consider a flip flop, mostly four transistors are required to build up one type of flip flop. Flip flop is the basic memory unit. By using that, we can store a one bit of memory, either zero or one. In digital system, we deal with the zeros and ones. So same concept is applicable here. If you like to go for system on chip design, that is SoC, so we can go for that. This is what the beauty of scaling down the nanoscale transistors. The transition from this diode to transistor, how this uh, journey uh, gives the innovation and revolution in the semiconductor industry. Just we will have a look over there. So this is the evolution of computer. We know the first computer ENIAC was manufactured with vacuum tubes. So large bulky tubes were there. If the large bulky tubes are there, so power required to drive that devices will be more. That vacuum tubes works as a memory unit for that particular first computer developed. After that, we came to know that we can modify that structure. We come up with the magnetic tape to store the memory. So next part in the picture is representing the magnetic tape for the storage devices. And after the invention of this transistors in the mid of 20th century, uh, we are able to get it done with the smaller structure of a computer. Previously the computer structure was very small. Now, right now, we are able to make that in our hand, whatever the devices we are having. So handheld devices, we are using the portable systems. So this is just because of scaling down the component size with the help of semiconductor manufacturing. We are going to minimize the size of component, and after that we can fabricate the IC of the complex circuit. And to make it the any type of electronics device, we can scale it down to the nanoscale. So this is a revolution of semiconductor industry. How it is useful? If you come to know the power down, power scaling we are achieving. This is the actual picture of first transistor made in 20th December 1947. The name of these three scientists, John Barden, uh, Walter Brattain, and William Shockley. These three person invented the world's first transistor. This news was published in New York Times, and this is innovation done by them in a Bell's laboratory. So this yellow structure you will find here. This is the first transistor structure they have invented, and from this moment, the revolution in the semiconductor industry starts. See, in 23 December 1947, these three people invented the first transistor in the world, and after the invention of this transistor, we are able to scale down, we are able to minimize the size of the devices. This is not stop at this moment, but ultimately in the history of IC, if you compare the size of a transistor which was invented in 1947,
Sir, we are unable to see slides.
you are not able to see the slides.
Yes, sir.
Right now it is okay.
Yes, sir. Now
Now
it is
okay.
okay. Yes, yes, sir.
Okay. For see, this is just because of limited connectivity in the net. If I am going to make it presentable with the F5 full screen, so some people might not able to see that. So please clear me. Right now the screen is visible for everyone.
Yes, sir.
Yes,
Okay.
sir.
Yes, sir. Yes, sir.
Thank you so much. Uh, you can see this first transistor. This is the actual picture of the transistor which was invented by these three, John, Bertrand, and William. The revolution in this era never start after 47, but in the year 1958, on 28th July, the first IC was monolithic IC was fabricated by the Jack Kilby, and for his invention he got a Nobel Prize in 2000. So this is the actual picture of the first monolithic IC fabricated by Jack Kilby with the help of one transistor, one resistor, and a capacitor. This is the first is a layout a structure he has created, and after that he has covered that IC, first IC, with some coating, outer coating to protect the protect it from the short circuit and give a insulation, robust insulation for that. So this is the history for how the semiconductor use of semiconductor for creating these transistors. And just a minute. Hello. Sorry for the interrupt. So this is the first IC. Uh, uh, After this, 1958, uh, commercial IC. So this is what the laboratory invention by the Jack Kilby to develop the first IC. After this, the marketable product, if you'd like to go for the uh, commercialize your product, so monolithic IC came in the market in 1961. After 58, the commercialization of that particular chip in this form. This is the internal structure of that particular first commercial IC. The cost of that IC was at that moment around $100. After that, whatever the derived form of the transistor, metal oxide semiconductor, complementary semiconductor, CMOS, in 1962 and 1963, and so on. So after this, the revolution comes in the electronics market, and we are able to minimize the sizes of the devices as the Moore's law. If you come to know that Morse, he was a statistician, scientist. He predicted that whatever the number of transistors you are going to integrate in a one package, that is IC, it will get double after every 2 years. That means after 24 months, the integration scale of a particular IC manufacturing will get double. So we can find out the rough scenario which is mentioned in this table. In 1950 to 1960, the scientists and innovators were able to integrate the 10 number of gates, logic gates, just like and or not, NAND gates, logic gates. So we are they were able to integrate up to 10 number of gates in a one chip, one IC. After this, in the 1970s, medium scale integration start, and they were able to 10 to 1000 gates in one single chip. In the 1980, they were able to get it done with the 1000 to up to 10,000 gates in one single package, that is LSI, large scale integration. In the 1990, the very large scale integration, more than 10,000 gates we can integrate in one single chip. After 2000, ultra large scale, million to billion number of gates. Again, 2010, giga scale integration. Now we are came to know the tera scale integration, and so on. So trillion number of gates. Whatever the circuit we have to design, we need to take a help of the transistor, RTL, DTL, transistor logic, TTL, diode transistor logic, DTL, ECL, emitter coupled logic. So the CMOS, complementary metal oxide semiconductor. So such type of the technology which the combination of transistor, diode, resistors, and capacitors. We are going to make the digitization of that. We are going to make a layout of that, and after that we are building the circuit, and how many gates we can integrate in one chip with that circuit. So this is the scaling of that gate in one chip. So Moore's law still going on. These are the different projected trends in IC design टेक्नोलॉजी. हमने डायोड से शुरू किया था. डायोड ट्रांजिस्टर का इंपॉर्टेंस सेमीकंडक्टर मैन्युफैक्चरिंग में क्यों है? तो डायोड एक बेसिक कंपोनेंट है इलेक्ट्रॉनिक्स का, जिसका हम यूज करके ट्रांजिस्टर बना सकते हैं. ट्रांजिस्टर के मॉडिफाइड फॉर्म जो है, वो ट्रांजिस्टर का टीटीएल लॉजिक गेट, ट्रांजिस्टर को लेके हम एक सर्किट बनाते हैं. कॉम्प्लीमेंट्री मेटल ऑक्साइड सेमीकंडक्टर, BiCMOS, silicon and insulator, FinFET, and beyond the FinFET. So all these are the different technologies for building one transistor, one circuit with three terminals. So basic element of all these things is a diode. So the invention start from the diode and come to the nanoscale transistor. That's why the webinar's name is given as the diode to nanoscale transistors. So diode is a basic element for building this all. So why, how we came to know that process technology and supply voltages. हमने पहले ही बता था कि जबकि हमारे पास फर्स्ट इन ए कंप्यूटर में हम वैक्यूम ट्यूब्स यूज करते थे. At that moment, the size of that vacuum tubes were very bulky, and we required higher huge power to drive that elements. If you are going to store one bit for with one vacuum tube, so it's not good in the current scenario to hold a large number of data, large amount of data in one package. So by scaling down all these things, we are minimizing the size of component. Ultimately, if you are able to minimize the size, the power supply required for that is going to be scaling down. So now we can able to minimize the size up to zero point 0.5 to 1.1 volt in this case. And after this, the handheld devices comes in the market after the invention of this transistor technology. Right now we are using mobile phone, smartphone, 5G, 4G. What is inside that? Inside that there is some PCB, printed circuit board, some components are placed over there, semiconductor diodes as well as some ICs. So how this revolution, all this just because of the innovation in the scaling down of the semiconductor manufacturing. Ultimately, uh, this is useful for the human being. So one once again, the same type of requirement, we can optimize the device in size, we can reduce the voltage, we can reduce the power consumption for that. The clock faster, we required a faster operation, that's why we required a higher number of crystals over there. So clock rate is also going to be increased with the help of this. The feature size is going to be down, minimizing the size. And ultimately, if you come to know what is the end product, how the semiconductor wafers actually look like. So this is the basic actual structure of a semiconductor silicon wafer. Whatever the horizontal vertical lines you are finding here, and the base, in a one square is nothing but a one IC, one chip. This is the actual picture of silicon wafer. Its thickness is 300 micrometer, diameter is 8 inch. Right now the new fabrication labs are using that 12 inch diameter wafers for the semiconductor manufacturing. अभी जितना भी बताया हमने कि डायोड ट्रांजिस्टर का जो यूज है वो सर्किट बनाने में होता है। उससे हम कोई भी एम्पलीफायर बनाते हैं, कोई माइक्रो प्रोसेसर बना रहे हैं, कोई अरिथमेटिक लॉजिक यूनिट बना रहे हैं, या कोई कस्टम एप्लीकेशन का आईसी बना रहे हैं, तो ऑल द सर्किट यू विल फाइंड हियर। अभी आपको जो ये सामने स्क्रीन पे दिख रहा है, दिस इज व्हाट अ ICs, whatever the square part in this wafer, circular wafer disk is there. So this is silicon wafer, and each square part is nothing but a one IC. अभी आप सोच रहे होंगे कि why I am showing this multi-layer metallization. What is the importance of multi-layer metallization in this semiconductor manufacturing? आपके पास पता है, आपके घर में अभी 4 लोग हैं, आपके एक 2 BHK होम है, 4 लोगों के लिए आपका 2 BHK सफिशिएंट है. If the number of members increase in your house, then what is the condition? What we generally do? Can we purchase the new land for these people? No. If you have already built a home with a 2 BHK, and we can extend that in a layer, we can put a first floor over there. So we generally prefer that. So this multi-layer metallization concept is came from this point of view. जैसे हम एक घर के लिए, हमारे पास एक घर है दो 2 BHK वाला, उस पे हम 8 लोग होते हैं घर में, तो हम ऊपर का एक मंजिला चढ़ाते हैं और उसके ऊपर एक मंजिला चढ़ा सकते हैं, जितना हमारा सिटी के लाइबिलिटी के हिसाब से हम 3 4 फ्लोर 5 फ्लोर तक के जा सकते हैं, उस हिसाब से हम उतनी मंजिलें चढ़ा सकते हैं, मतलब स्पेस हमारा उतना ही रहेगा। लेकिन हम क्या कर रहे हैं, मंजिल चढ़ा रहे, उसी स्पेस में हम कॉम्पैक्ट करके नंबर ऑफ लोगों को ज्यादा ठहरने की जगह दे रहे। सेम फिनोमेना इज नथिंग नोन एज अ मल्टी लेयर मेटलाइजेशन। इतना ही चिप का एरिया है, उसी एरिया को हम एक्सटेंड करके लेयर में कनेक्टेड वायर्स के द्वारा उनको एक दूसरे के साथ अटैच करके रख रहे हैं। दिस इज द concept for the integrating the n number of components in one single package. This is all about the history from diode to transistor and vapor manufacturing, how the process is going on. Now we will come to the main part, what is meant by domains and what is meant by platforms. As a student point of view, what are the different domains in semiconductor manufacturing? You must be aware about that. What are the different software and hardware platform required to learn so that you will get opportunity to enter in this semiconductor manufacturing? As an employee or as a manufacturer, you can play any type of role. So first thing, we will go for the domains. Digital domain, if you'd like to process or would like to manufacture a processor, memory unit, or other digital circuits. The circuit, electronic circuit, which works on the DC supply. In simple language, we will say that digital circuits. Digital having only two states, either 0 or 1, logic 0, logic 1. So if you'd like to manufacture that type of component, that type of unit, then you have to deal with the digital VLSI. If the components are running on the analog signal, just like amplifier and oscillators, it requires an analog signal to run the different signal processing of audio, speech signal, video signal. So we would like to go for that type of circuit design, so it comes under the analog VLSI design. If you have a mobile phone like device which is having internally digital as well as the analog, both the components are available, so mixed type of signal, so we have to go for the mixed signal VLSI design. That means in that case you have to write a code or make a schematic layout of transistors uh, in a mixed mode domain in combination of digital as well as analog. If you'd like to design an amplifier and radio transmitter, receiver, wireless communication system, just like Wi-Fi and or the routers and these things, a baseband processor having some trans receiver or a solid state antennas are manufactured in a smaller scale in a mobile. So if you'd like to go for the radio frequency, then we have to deal the another technology, that is RF VLSI technology. If you like to go for the power management, we have to focus only on the distribution of the power in the voltage regulator as well as the converters and battery management system. Right now we are moving to the electric vehicle, so at that moment this type of all mixture comes into focus and we need to deal with all technology. So that's why uh, during COVID we face uh, delay in the delivery of the cars. So many manufacturers stuck in India because they are assembly plant and some semiconductor control devices, that is electronic control unit, as well as the uh, some controlling parts inside the vehicle. They came from the outside India, and manufacturing during that COVID was not possible. That's why we get delayed in the delivery of the vehicle, and the dealer says हमारे सेमीकंडक्टर का डिले है, उसकी वजह से लेट हो रहा है, सेमीकंडक्टर अभी नहीं मिल रहा है हमको. तो दिस इज व्हाट द रीजन. दीज आर द डिफरेंट डोमेन्स. मीन्स जैसा हमारा एप्लीकेशन है, डिजिटल एप्लीकेशन है, डिजिटल सर्किट बना रहे तो डिजिटल डोमेन, एनालॉग सर्किट तो एनालॉग, मिक्स है दोनों तो मिक्स, रेडियो फ्रीक्वेंसी ट्रांसमिशन रिसीव कर रहे हैं, एम्पलीफायर बना रहे हैं, फ्रीक्वेंसी सिंथेसिस, देन RF. If you are dealing with the power management regulator, voltage converters, then power domain. अभी ये सब चीजों को कैसे बनाते हैं, इसके लिए हमें लगते हैं प्लेटफॉर्म्स. तो प्लेटफॉर्म्स जो है हमारे सॉफ्टवेयर फॉर्म में इलेक्ट्रॉनिक्स डिजाइन ऑटोमेशन के टूल्स है. द फर्स्ट टूल इज मोस्ट इंपॉर्टेंट एंड वर्ल्ड वाइड यूज, दिस कैडेंस सिस्टम डिजाइन. कैडेंस में जो है वो सारे के सारे एनालॉग डिजिटल RF, वी कैन डिजाइन एनी टाइप ऑफ डिजिटल VLSI प्लेटफॉर्म इन कैडेंस डिजाइन सूट. सिनॉप्सिस है, सिनॉप्सिस के बाद में मेंटर ग्राफिक्स है, विच इज राइट नाउ Siemens business. Mentor graphic is hired by the Siemens, so it is now Siemens. ANSYS है, ANSYS में HFSS से आप इलेक्ट्रोमैग्नेटिक सिमुलेशन करते हो, उसका जो इंटीग्रेशन करके आपका सर्किट बनता है कोई RF सिग्नल का, तो यू कैन गो फॉर दैट फॉर द सिमुलेशन एंड एनालिसिस ऑफ दैट RF components, RF signal, RF antennas, all these things, and the semiconductor manufacturing is going to integrate that in your product. So Keysight is the company. Formerly it is a Agilent. This also offers some software tools for all these designs. अभी सॉफ्टवेयर तो नाम पता हो गया हमें, हार्डवेयर कैसे है, मतलब हार्डवेयर जो है. So to manufacture one single IC is not possible. The cost of single chip, if you have a circuit, आपने एक सर्किट बनाया, वो एक इनोवेटिव सर्किट है जिसका आपको चिप बना के होना है. So at that moment, you can't go for that direct chip. We required some foundry टेक्नोलॉजी फाइल, दैट इज हमने जो बोला ना कि हम नैनो स्केल पे आ गए हैं, नैनोमीटर टेक्नोलॉजी पे हम काम कर रहे हैं, 0.7 माइक्रो नैनोमीटर, 5 नैनोमीटर. सो इफ यू आर गोइंग फॉर दैट, so then we required a one technology file which is imported from the foundry. फाउंड्री मीन्स फैब्रिकेशन लैब. जो अभी हमारे आज की तारीख में जो हमारे ऑनरेबल प्राइम मिनिस्टर ने फैब्रिकेशन लैब, 3 सेमीकंडक्टर फैब लैब्स, 1.25 लाख करोड़ रुपए का इन्वेस्टमेंट करके 3 जो लैब बना रहे हैं, वो वही लैब से आएगा. जितना टेक्नोलॉजी पे हम, मतलब जितनी स्केल पे वो वेफर बना सकते हैं, उसके कुछ स्पेसिफिकेशन होते हैं. अकॉर्डिंग टू दैट स्पेसिफिकेशन वी नीड टू डिजाइन आवर सर्किट. हम कोई और टेक्नोलॉजी का सर्किट बनाते हैं जिसका थिकनेस ज्यादा होगा, वेरी होगा, वैसे नहीं होता. इसमें इसमें वी नीड टू आस्क फर्स्ट द फैब्रिकेशन लैब, what is the technology file you have available. On the basis of that we are going to build our circuit for compatible with that technology. नहीं तो हमारा उसका थिकनेस अलग होगा, उसको 300 माइक्रोमीटर का ही वो थिकनेस का आईसी बना सकता है, और हम उससे भी स्केल डाउन जा रहे हैं और हमारा सर्किट उसको फैब्रिकेशन के लिए भेज रहे. सो इट इज नॉट पॉसिबल. सो दिस इज व्हाट द बेसिक कंडीशन. सो ये सब चीजें जो है हमें ये सॉफ्टवेयर में पहले करनी पड़ती है. अभी सॉफ्टवेयर में हर एक को पॉसिबल नहीं है कि एक सिंगल चिप मैन्युफैक्चर करे. तो व्हाट इज द सॉल्यूशन? वी हैव सम हार्डवेयर प्लेटफॉर्म्स विथ दिस हार्डवेयर डिस्क्रिप्शन लैंग्वेजेस. अभी ट्रांजिस्टर लेवल पे एक डिजाइन बन के हमारा पूरा सर्किट हो सकता है. सेकंड पार्ट है हमारा हार्डवेयर डिस्क्रिप्शन लैंग्वेज. जस्ट लाइक हम C++ सीखते हैं ना, तो सी से हमने सिस्टम सी डिराइव किया है, जो कि ये सिस्टम लेवल मॉडलिंग कर सकता है, जिससे हम एक्चुअल सिस्टम लेवल आर्किटेक्चर बना के उसको हार्डवेयर में इंपोर्ट करके उसको टेस्ट कर सकते हैं. We have some hardware platforms also. So Verilog, VHDL, System Verilog, System C, VHDL, ASM. These are the languages, just like a C++, Java. You have to learn this language for the digital as well as some Verilog is used for some time mix modeling too. नहीं तो हमें डिजिटल का सर्किट बनाना है तो हम इससे बना सकते हैं. लेकिन इफ वुड लाइक टू गो फॉर द एनालॉग सर्किट, तो उसके लिए ट्रांजिस्टर लेवल मॉडलिंग करना पड़ता है. जो सॉफ्टवेयर में हमारे कैडेंस वाले जो है, कैडेंस मेंटल ग्राफिक्स, उसमें हमें ट्रांजिस्टर लेवल लेआउट बनाना पड़ता है, और उसके बाद ही हम उस आईसी के मैन्युफैक्चरिंग की प्रोसेस के लिए जा सकते हैं. सो दीज आर सम हार्डवेयर प्लेटफॉर्म. By using this hardware platform, we can get a prototype of your actual fabrication. Instead of going to the actual technology fabrication, we are not able to get it done with that file. कोई फैब लैब आपको इजीली वैसे देता नहीं. we need to purchase that, we have to pay for that. Around 2 to 5 lakhs वन सिंगल आईसी अगर फैब्रिकेट करना है ना, तो 2 से 5 लाख रुपए खर्च आता है, ये फर्स्ट सिंगल के लिए. लेकिन इफ यू गो फॉर द लार्ज एन नंबर ऑफ आईसीज, देन इट इज came down to the minimum some pesos. In 1 rupees you can get one IC. So these are the some hardware platforms. By using this you can easily get it done at the your prototype. अगर आपने एक ऑपरेशनल ट्रांसकंडक्टर एम्पलीफायर बनाया है, या तो फिर एक आधा सपोज आपने एक कोई डिजिटल सर्किट बनाया है कि जो मार्केट में अवेलेबल नहीं है, लेकिन कोई कंट्रोलिंग पार्ट के लिए आपका वो डिजिटल सर्किट यूज होता है, आपने VHDL वेरिलॉग लैंग्वेज सीख के उसका यूज किया है, तो आप with the help of this EDA tools which were mentioned in previous, this synapses, mental graphics, Xilinx also there. So Xilinx के EDA tool लेके आपका Xilinx का FPGA field programmable gate array and complex CPLD, complex programmable logic devices, CPLD. These are the two embedded platform. This comes under the embedded technology of the VLSI domain. Okay. सो ये प्लेटफॉर्म लेके हम उससे प्रोटोटाइप बना के आपका चेक कर सकते हैं फंक्शनैलिटी ऑफ योर डिवाइस. So these are the some hardware platforms: Xilinx, Intel, Lattice, Microchip, Actel. अभी ASIC डिजाइन जो है, ASIC डिजाइन मीन्स एप्लीकेशन स्पेसिफिक इंटीग्रेटेड सर्किट. ये वाले पहले जो प्लेटफॉर्म है, these are the generalized platform. We can dump your code inside that hardware. You can erase that. Once again, you can get some another circuit. You can dump it. You can test it. You can again erase that. But if you go for the application specific ICs, if you don't have enough fund to go for the manufacturing technology, तो उस टाइम में हमें क्या होता है, कुछ ASIC के ICs मिलते हैं जो वन टाइम प्रोग्रामेबल होते हैं. विद द हेल्प ऑफ EDA टूल्स एंड हार्डवेयर डिस्क्रिप्शन लैंग्वेजेस, आपका जो सर्किट बना है, you can go for that. You can directly dump that into the application specific ICs. You can test it. It is a one time fusible ICs. One time उसको फ्यूज हो गया, बाद में यूज नहीं होगा, erase नहीं कर सकते. So ASICs is a different for the if you are able to make it, then it can be portably and use in different applications. मुझे फैब्रिकेशन लैब का जो आपका जो कॉस्ट है उसको मिनिमाइज करने के लिए n नंबर ऑफ वेज आर देयर. अभी टेस्टिंग के लिए स्टैंड अलोन एप्लीकेशन कोई अगर चाहता है कि हमने ऐसा एक नया बनाया, उसको हम टेस्ट करके पेटेंट कर सकते हैं. आईसी नहीं होगा तो पेटेंट कैसे होगा? आपका सर्किट पूरा कंप्लीट नहीं होगा, डिजाइन पेटेंट बनाना है तो आप ऐसे एफपीजीए पे लेके उसको टेस्ट कर सकते हो. वन टाइम प्रोग्रामेबल ASIC के रेडीमेड आईसीज मिलती है, उसको भी आप कर सकते हो. और एप्लीकेशन स्पेसिफिक आईसी जो है, ये डीएसपी प्रोसेसर्स वगैरह जो है, दिस इज वन एग्जांपल ऑफ एप्लीकेशन स्पेसिफिक आईसीज. सो दीज आर द सम एडवांटेजेस ऑफ VLSI. डिजाइन साइकिल टाइम रिडक्शन होता है. एक बार आपका चिप का टेस्टिंग हो गया सॉफ्टवेयर फॉर्म में, इट गोस फॉर द वेरियस टेस्ट. डिजाइन टेस्ट उसमें होते हैं, पावर एनालिसिस होता है, एरिया ऑप्टिमाइजेशन, पावर ऑप्टिमाइजेशन, कॉस्ट. अल्टीमेटली एरिया ऑप्टिमाइज हो गया तो कॉस्ट भी ऑप्टिमाइज हो जाएगा, क्योंकि सेमीकंडक्टर का पर चिप का पर स्क्वायर मीटर के हिसाब से प्राइसिंग लगता है. जितना स्क्वायर मीटर का आपका एरिया होगा उस हिसाब से आपके चिप का रेट होगा, ना कि आपके इंटीग्रेशन से. एन नंबर ऑफ कंपोनेंट कितने हैं वो नहीं पता, उसके हिसाब से एरिया और वो एन नंबर ऑफ कंपोनेंट्स, उससे आपका चिप का मैन्युफैक्चरिंग कॉस्ट बढ़ता है, कम होता है. वी आर एबल टू गेट इट द रिडक्शन इन द साइज. पावर कंजप्शन कम हो रहा है, अल्टीमेटली कॉस्ट कम हो रहा है. ऑपरेटिंग स्पीड बढ़ रहा है, क्योंकि हम नैनो स्केल में जा रहे हैं तो हमारा फ्रीक्वेंसी बढ़ रहा है. फ्रीक्वेंसी बढ़ रहा है मतलब ऑपरेटिंग स्पीड बढ़ रहा है. डिवाइस सिक्योरिटी, वी कैन इंटीग्रेट n number of component and make it compact and secure. Along with the security system, we can go for the encryption. We are going to increase the productivity, design flexibility है. And ultimately, if you come to know this journey from diode to transistor and different EDA tools, this is the what end product आपके हाथ में जो आता है ना, final, that is your integrated circuit, that is IC. There are some issues and challenges in this technology. Rate of change of technology versus design cycle time. Suppose अभी आप 130 नैनोमीटर पे काम कर रहे हो, और तो मार्केट में जो है नए प्रोडक्ट जो आते हैं उससे भी कम आ जाते हैं. मतलब टेक्नोलॉजी स्केल डाउन हो रही है. हमने अगर कोई सोचा है कि हम इतने ज़्यादा थिकनेस पे काम करेंगे, हमारा वेफर इतना है, तो 2 साल के बाद में आपका जब तक प्रोडक्ट्स का लाइफ साइकिल खत्म होगा, आप इन्वेंशन करोगे और उसको प्रोडक्ट मार्केट में सोचोगे, तब तक दूसरा कोई उससे भी स्केल डाउन में आपका प्रोडक्ट लाएगा. These are the some challenges. Feature size, modeling and testing, speed versus power testing. These are some challenges, issues. टाइम टू मार्केट, आपका जितना ही जल्दी मार्केट में आएगा उतना ही बेनिफिट होगा. जितना लेट, क्योंकि मूर्स लॉ के हिसाब से हर 2 साल के बाद में इंटीग्रेशन डबल होगा. मतलब आप एक टाइम पे आज की तारीख में अगर सोचा और आपने आपका प्रोडक्ट बनाने में 2 साल लगा दिए, तो आप जिस तरीके से आप सोच रहे हैं और जितना स्पीड है मार्केट, टाइम टू मार्केट योर प्रोडक्ट, जितने जल्दी वो आएगा उतना फायदा होगा। नहीं तो फिर आपका जब तक प्रोडक्ट आएगा, आपके टाइम पे दूसरा कोई मार्केट में उतना प्रोडक्ट लाएगा जो आपसे भी डबल स्पीड देगा, डबल पावर, लेस कंजम्पशन देगा। दिस इज द फ्लो in field programmable gate logic. So there are some steps we need to follow. फर्स्ट हमें डिजाइन का स्पेसिफिकेशन जो होता है वो स्पेसिफिकेशन लेने पड़ते हैं। वी कैन गो फॉर डिजाइन with the help of hardware description languages like VHDL, Verilog. We can go for the RTL schematic. uh, with the help of the NAND gates, NOR gates, we can design a schematic. Or finite state machine, we can draw a state diagram. If you'd like to go for the algorithm, I have some algorithm, I need to go for that algorithm and I have to implement that in a IC. So for that, finite state machines are useful. Then we need to go for the functional simulation. रजिस्टर ट्रांजिस्टर लेवल मॉडल, आरटीएल स्कीमेटिक जो है उसका, जो भी आप कोड लिखोगे स्कीमेटिक से या फाइनल स्टेट मशीन से, उसका आरटीएल मॉडल बनेगा। उसके बाद में आपकी फंक्शनल टेस्टिंग होगी, उसके फंक्शनल सिमुलेशन, हाउ इट इज गोइंग टू बिहेव, व्हाट इज द इनपुट, आफ्टर दिस इनपुट व्हाट विल बी द आउटपुट, वेदर इट इज ओके, देन वी कैन गो फॉर द सिंथेसिस। सिंथेसिस के बाद में उसका गेट लेवल कन्वर्जन होता है, उसका नेट लिस्ट होता है, उसके बाद में टाइमिंग सिमुलेशन होते हैं, करेक्टनेस ऑफ द आउटपुट, गेट एंड इंटरकनेक्ट का जो टाइमिंग सिमुलेशन है, मतलब जितने नंबर ऑफ का आपका सर्किट बना है गेट लेवल मॉडल, जो भी आपने वेरीलॉग स्कीमेटिक और एफएसएम फाइनाइट स्टेट मशीन से बना है, उसका स्कीमेटिक लेके आपका मैपिंग एंड ट्रांजिशन का जो स्टेट होता है, उसके बाद में हम क्या करते हैं, एपीजीए वगैरह सीपीएलडी जो डिवाइसेस है ना प्रोटोटाइपिंग के, मैंने अभी पहले बताया, यू कैन गो एंड चूज दैट हार्डवेयर, कि जिस हार्डवेयर में हमें उसको इम्प्लीमेंट करना है उसको मैप करना पड़ता है कि एन नंबर ऑफ गेट्स अवेलेबल इन दिस एफपीजीए सीपीएलडी। सो उसके हिसाब से हमारा सर्किट जो बना है उसके उससे ओवर हो रहे या अंडर है, तो कितना एरिया उसको लगेगा, इट मैप्स इन दिस मैपिंग एंड ट्रांसलेशन। एंड व्हेन we came to know ki yes, we are going to fulfill the requirement, we can place and route that soft form into the hardware form, and then choose the program generation, bit file generate करना है, और उसको with the help of JTAG serial communication or parallel communication you can impose that design and take an embedded device ready with the field programmable gate array or CPLD devices. In short, we are going to brief out the journey from diode to transistor and this semiconductor manufacturing. This is what uh, a bit chunk and introductory part to this session. So with this, I would like to conclude here today's session. In a very hurry, I have sum up all these things, journey from diode to transistor. If you have any question, I would like to ask any question, please. Hello.
On this, like, just kind. Okay, okay, okay. Students over there in the online, if you have any doubts, you can be clarify with Dr. Arun sir.
Language doesn't barrier,
Sir,
huh? Hindi,
you have
Marathi.
been clarified everything well, and therefore I hope there are not any questions from the student side. And at the outset, let me thank personally from on behalf of Regional Center Nagpur for your time and then your expertise over there in the field, and then giving a wonderful lecture. Uh, the learners sitting over here are heterogeneous students of different faculties, and even for the layman like me, the concept which you have been made very clear. And thank you so much for you for taking a wonderful session today morning, and then given a good lecture to us. And I also thank Dr. Lakshman Kumar Vatsal, the regional director of Austin Nagpur, for identifying such a wonderful resource person that can be reached almost all the students category, like disciplines from multidisciplinary students. So that was one a potential of Dr. Kumar Wat sir to identify the right resource person for the right program, and I thankful to Dr. Kumar Wat sir. And I also thank Dr. Prabha Madam, who has been arranging this online and offline program over here at Sevadal Mahavidyalaya. And I thank Mr. Rajesh Vasnik, Mr. Rajgure, and other the faculty members of this college and the management of Sevadal Mahila Mahavidyalaya for arranging this wonderful session. And I thank all the students over here sitting for the entire 1 hour, and then patiently listening the lecture, and so curious to be attend the sessions. And thank you so much. Thank you all. Thank you, sir. Dr. Arun sir, thank you. Thank you for your wonderful session, sir.
Thank you, Shashikumar sir. Thank
Ji.
you.
Yeah, thank you. Thank you, sir.
Still, if you'd like to know anything more, if your students are having some queries, you can note down my email ID as well as mobile number. You
Fine,
can
sir.
contact me anytime for any type of help to the student regarding the career opportunity, how to approach to the different softwares, how to get it done, prototyping to efficiency PLDs. I will be always ready with IGNOU as well as the associated colleges with IGNOU and other. You are from Cochin, sir? I think so.
Oh, thank you, sir, for your positivism, sir. Definitely, we'll be in touch with you, and then yes, our young learners who have been completing the program, definitely any academic support required from your side, let you know, sir. And thank you so much, sir. Thank you.
Thank you, sir.
Okay.
राजगुरे सर, तिकडे काही क्वेश्चन आहेत
नहीं
मुलांना?
questions अभी नहीं है, I think, sir. You have been explained well, sir. So therefore, there was no questions from the learner's side, sir.
Okay, okay. Thank you so much, sir.
Yes, sir.
I would like to say thanks to Nagpur regional team IGNOU, all the faculty members as well as the enthusiastic students. I hope whatever the basic information regarding this semiconductor manufacturing I have explained, uh, hope it has given you the chunk of that how this semiconductor manufacturing going on and how it is useful for the society as well as the nation. So from my side, it's over, sir. Thank you, Dr. Kumarwad.
Kumar, sir,
Thank
if
you,
you
sir.
want to say something from your end, you can say something, sir.
No, 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 no. Very wonderful session. Thank you, Dr. Arun.
Okay, sir. Thank you.
Fine, sir. Thank you. Thank you so much, sir. Thank you. We'll meet in
Thank
some.
you.
Thank you.
Sure, sure, sir. Thank you.
Great, sir.